This is the second hour of Physics 1B for October 4th. And we're still talking about heat transfer, and what we're going to do is we're going to try to solve this problem right here about conduction into a picnic cooler. And we're going to try to make use of this equation to do so. So let's scroll down a little bit and make some room. And let's copy this one down to here. And we're going to need this data, but we'll just scroll up and get the information that we need for our problem. So here's the problem. Make it bigger so you can read it, hopefully. If I need to make it bigger than that, just say something in the chat. All right, it says a styrofoam cooler has a total wall area, including the lid, of 0.8 meters squared. So I guess that means that if you take into account, it's a cooler, you take into account all the walls and the top, you get 0.8 meters squared. The thickness of the walls is 2 centimeters. It's filled with ice water and cans of Omni-Cola, all at 0 degrees Celsius. What is the rate of heat flow into the cooler if the temperature outside the wall is 30 degrees Celsius? And how much ice will melt in 3 hours? Okay. So, okay, they've drawn a picture for us here. I guess that picture's fine. Just to be more clear, the idea is that, so we've got our cooler, and the idea is that the whole area of the cooler, the surface area basically, total surface area, is 0.8 meters squared. But we're just going to use, we're going to act as if that's only one side, just for the simplicity of using this equation. And that's why they've reduced the whole thing down to this picture here, where you have the temperature on the outside. So this is the outside air, and this is the side where the cooler is. So the cooler's got the ice and the cola in it. It's at 0 degrees Celsius. The side on the air side has a temperature of 30 degrees Celsius, which is like in the 90s, I think. Maybe the high 80s. And we've got the area. So this is definitely one of those plug and chug problems where it just asks us first to find what is the rate of heat flow into the cooler if the outside wall is 30 degrees Celsius. So that's pretty straightforward. We just have to say the heat flow, which is dq dt, or h, should be equal to, we take K, which is going to be the thermal conductivity of the material. This is going to be the thing that we need to find K for. It's made of styrofoam, right? So we're going to have K for styrofoam right here. We have the area of the cooler, and then we've got the hot temperature, TH, minus the cold temperature, TC, and then L, which is this right here. So we have all the data, and we can plug everything in. We just need to go look up KS in the table, right? So 2 centimeters is L, except that's going to have to be converted into 0.02 meters. 2 centimeters, I guess that's a pretty normal size. Everything else is labeled though, right? TC is here, TH is here, A is here, L is here. So let's go look up what the conductivity for styrofoam is. It looks like it's 0.027. Are there any? No, it's just 0.027. So it's 0.027 watts per meter Kelvin. Let's write that down. We just plug everything in. At least for part A. If you all want to tell me what you get if you plug everything in as I'm writing it down, that would definitely help. Alright, the numerator, TH minus TC. So it's 30 minus 0. I will say, because we're dealing with temperature difference here again, this K from that definition can also be written as degrees Celsius. Just so you don't have to always convert. L is 0.02 meters. Let's see, 30 times 5 times 100. So 30 times 500. It's 15,000. Yeah, 15 times 27, that's a hard one. But it's like 3 over 2. 3 times 27 would be, I don't know, 81? What do you all get? 32 point... Yeah. That sounds like a good number. So it's 32.4. What are the units on this going to be? Well, we can check. It looks like the degree Celsius cancels out with the degree Celsius. The meters cancel out with the meters. And so we get watts. Does that seem reasonable? Well, a watt is the same thing as, just to remind you, a joule per second. So I'm pretty sure that this seems pretty reasonable, right? Because it's heat per second, so it seems reasonable that it would be joules per second, or watts. So there we go. That's the rate of energy flow into the cooler. I did leave out the area. Thank you, Mr. Wynn. I did leave out the area, so we should have multiplied this times 0.8. That answer that you all got, was that including the area? Even though I forgot to write it in there? It's easy enough to calculate it. It is? Okay, cool. If not, it would just be 80% of whatever that answer was. I'm just going to check for good measure. Times 30, divide 0.02 times 0.8. These are the best kind of physics problems, and Physics 1B is full of stuff like this, which is really good. The next part of it is to find how much ice melts in 3 hours. So, to get a better understanding of how much heat is actually flowing into this, let's transfer into something we can understand, which is how much ice melts, because I don't know what 32.4 watts means, you know? Like, is that a lot? Is it a little? Are my sodas going to get really hot really fast here? I don't know. So, let's figure it out. How would we do that? How do we find how much ice melts in 3 hours' time? Is it going to be all of it? Can we just say all of it? Do we need to do it? Or do we need to calculate something? Convert seconds to hours. Yeah, I mean, that's definitely something we're going to have to do. Find Q first. What's Q? What do you mean, Richard? Find the amount of heat? Find the amount of heat that's transferred in 3 hours? Is that what you mean? How would we do that? How do we figure out, if I know that there's a rate of heat flow at 32.4 watts, and I want to figure out how much heat actually flows into the system, how would I do that? We take I think that's close, but you mean to say that H is Q over T, so that means that Q is going to be H times T, right, Richard? Okay, that's fine. That's fine. You want to fix it? You can edit it, and you can fix it, just so that it's there and people can see it. And then when UN also says that we need to find the total heat flow in 3 hours. That's right. So the way we can do that is we can say we have the rate at which heat is flowing into the system. And so if we take that and you multiply by 3 hours, and of course then we also have to convert the hours into seconds, and I think that 1 hour is 60 times 60, or 3,600 seconds. That should give us the quantity of heat that actually flows in, right? So all we got to do is just put 32.4 joules per second, and then multiply by 3 times whatever, all this stuff. All right, what do you get? What do you get for Q here? Just barely enough room to write this. Can we call it 350,000? Is it 349,920? So 350,000 is probably good, right? Just a nice round number. And again, this is the thing about physics, is like, I can see that number and you can see that number, but we don't really know what a joule is, right? I mean, I don't know what a joule is. I know what it is. I can tell you lots of things. It's a measure of energy. It's a kilogram meter squared per second squared. But when I see 350,000 joules, I don't know what that is, right? If I see a gallon, and you tell me you have a gallon of milk, I can visualize what that is, right? But visualizing a joule is a lot harder. So how do we now figure out how much ice melts? Because that's what we wanted to figure out. If we have the heat transfer, how do we find out how much ice melts? This part's kind of easy, but maybe it's not. I don't know. Can we sum the Q of the phase change and set that equal to Q? Yeah, we can use the phase change. The all those things are right. Yep, exactly. So we know that this Q is going into the water, or into the ice. So what we can say is that if I do Q equal to the mass of ice times the latent heat of fusion for water, then I can figure out what mass of ice will melt by solving this by just taking Q and dividing by the latent heat of fusion of water. So that should give us the amount of ice that melts. Do we know how much ice there is in there? Or does it just say it's filled with ice? Yeah, so we have an unlimited quantity of ice to melt. So let's figure out how much actually melts. So Q was 35000 joules. And the latent heat of fusion, I think it's 233,000. Let's look. I don't remember. We used it in the first problem. No, it's 334,000. 33400. So we're just using the latent heat of fusion for water. 334,000. The interesting thing is that even with 350,000 joules, which if you have 350,000 of anything, it sounds like a lot. But it's not that much energy, at least in terms of melting ice. It looks like the answer is going to be about 1, right? A little over 1. A little over 1 kilograms. Oh my god, I've gotta close my email. It's beeping at me, and that's probably being picked up on the recording too. All right, what do you all get as your answer? Let's see. It's really close to 1. .05 kilograms. That's a lot of ice, actually. Kilogram of ice is a lot of ice, right? Is it? I don't know. How many kilograms of ice are there in like a bag of ice? You could buy a bag of ice, it's probably like 3 pounds, 5 pounds, something like that, I guess. A few kilograms, I guess. So let's think about what we did here. So we looked at a problem where there was a styrofoam cooler, right? The styrofoam cooler had ice cubes in it, and it's closed. And what this problem is about saying that, yeah, you have a cooler and it's got your colas in here and it's got all your ice and stuff like that. The cooler is not perfect. It's not a perfect insulator, right? It does have heat exchange with its environment. It's just that heat exchange is extremely slow. And why is it slow? Well, because of this number right here. If we replace our cooler with a metal box or something like that, then the amount of ice that melts is going to go way up, because this quantity is the main thing that's slowing things down, right? This is the conductivity of the styrofoam. If you look at something, for example, like brass, which has a conductivity of 100, I mean, how much more is that? Let's see. It's a lot faster. I don't immediately see how faster, but it's a lot faster. Is this comparable to IRL coolers? 3 hours seems like not a lot of time. Yeah, I would agree. So what's going on here that's making this... okay, let's think about it like this. Let's think about this like kind of as an engineering kind of thing. What could we do with our cooler to make it better? I agree with you. I don't know if it's comparable. I will say that, like, yeah, I mean, if you get a cooler and you put it outside in the hot sun, you know, and it's like you're on the beach or something like that, the ice is going to melt pretty fast, right? Keep in mind, by the way, Christian, this is only 1 kilogram of ice. And I was thinking, like, if you had an actual cooler and you filled it with ice, you'd probably have maybe like 3 or 4 kilograms of ice in there, depending on the size of the cooler. So all it's saying is that only 1 kilogram of your ice is melt, which that seems logical to me because, I mean, just think about anytime you've been somewhere where you had a cooler, like at a party or something like that, and it was outdoors. You know, you open the cooler, you go in there to get a beverage of whatever type, and it's usually a combination of ice and water, right? Because some of the ice ends up melting, right? So this seems pretty normal. Yeah, I think it's pretty normal. Because yeah, you could say, oh yeah. So what could we have done to make this thing better at keeping our ice from melting? What could we do? What are increase the length? Yeah, that would have a huge effect, right? If we just double the thickness of our walls right here, you're going to get half the heat transfer, right? Because it shows up here in the denominator. right? So if we just make the walls thicker, that'll work. This is why when you go buy styrofoam, when you go buy like a styrofoam cooler from the store, they have really thick walls, right? So hopefully that makes sense as to why now. Even though you could also just use logic, I think, to understand why thicker walls is better. But anyway, what else can we do? What else could we do to prevent this this from melting so fast? Christian, you said make it smaller. You mean make the cross-sectional area smaller? The area of the outside smaller, I assume? Yeah. Yeah. That would work. And that's really all we can control. The only other thing that we can control is the substance that we're using right here, right? So we could switch to a substance that has a higher insulation, a lower conductivity. Like, I don't know, let's see. What's the only things that are smaller than this are, there's not much. Argon. There we go. You could have layers of like styrofoam filled with argon. That would make it even better. It's probably kind of difficult to acquire argon, I would bet, though. All right, that is just one type of problem that you can solve with this. Are there any other questions before we move on? We're gonna do one more. Bury in the dirt. That's clever. Yeah, exactly. So you could prevent it from being in contact with the hot air by like digging a hole. Yeah, and putting it in the dirt. That's smart. I like that, Christian. That's really smart. Yeah, surround it by the coldness of the earth, and it'll only transfer heat through the top. That's a good point. All right. Oh, there it is. I was like, where is this problem? All right, now we have two different objects. Okay, let's grab our formula right here. All right, so now we have a steel bar. It's 10 centimeters long. It's welded end to end to a copper bar that's 20 centimeters long. So you can see the picture right here. So we have a steel bar here. We have a copper bar here. They're welded end to end like this. Each bar has a square cross section. So they're kind of shaped like rectangular prisms with the interface here being a square. It's 2 centimeters on a side, which means the area is going to be 2 times 2. So the area is going to be, it's 2 centimeters on a side for the square, right? So you have to take 0.02 meters, and then you have to square that, which is 0.0004, I think, meters squared. So that's our cross-sectional area A. The free end of the steel bar is kept at 100 degrees Celsius by placing it in contact with steam. So we've got steam over here, 100 degrees Celsius. And the free end of the copper bar is kept at 0 degrees Celsius by placing it in contact with ice. So this is cold side over here, hot side over here. Both bars are perfectly insulated on their sides. Perfectly insulated, which is impossible to achieve, means that they're not going to lose heat to their environment, basically. I.e., they want you to think about the problem only in terms of the heat transfer that occurs through the bars themselves. We want to find the steady state temperature, okay, at the junction of the two bars and the total rate of heat flow through the bars. So we want to find how much heat is flowing. It has to flow this way, right? That's the heat flow, Q. And we also want to know what is the temperature at this location equal to, right where they're contacting each other. Does the problem make sense? What do we do? How do we solve this? Quite a bit trickier than the previous problem. This steps beyond the plug and chug into the realm of you need to think about things. you think maybe we could split it into two different heat transfers? Okay. What would that look like? How could we describe what those two heat transfers would be? H steel plus H copper equal to 0. Okay, I'll write that down. Let's see if that makes sense. So if we want, you want to say basically that if we take the heat transfer through the steel plus the heat transfer through the copper equal to 0. What do you all think? Does that make sense? Can we do that? We can try. We might as well. Let's give it a shot. Let's see what happens here. So. And let's also try to figure out for ourselves if this is a reasonable thing to assume. It could just be that we have to make this equal to the total heat transfer, you know? Because ultimately, there is a rate of heat flow. Let's just do it like this. Let's start off by just seeing what happens if I write these two equations down, and let's just play with it and just see how we can develop an idea of how to solve it out of that, not knowing what the sum is equal to. But I think assuming that it's equal to 0 might be reasonable. Let's think about that. Certainly the case that once the equilibrium condition has been reached, once we reach the steady temperature, no, there's still heat flowing, right? There's still heat flowing because this is hot and this is cold, so there's always going to be heat flow, right? So I don't think it can sum to 0, but let's write this down. All right, so H from the steel. So we're going to have K steel times the area times TH minus TC. So what I'm going to do is I'm going to say for the steel, the hot point is here, and the cold point is right here, basically, right? So it's going to be, the hot side is going to be 100. I'm just going to put numbers in here because I think it's a lot easier to do that. Minus, the cold side is going to be the common temperature T in the middle, and then we need to divide that by the length of the steel. Plus, same thing for copper, so we have K for copper times the area times, for the copper, the hot side of the copper is going to be right here, and the cold side of the copper is going to be here at 0, so it'll be T minus 0 divided by the length of the copper. So we notice that we have this equation. It only has one unknown in it. Actually, it's not an equation yet, it's just an expression because it's not related to anything. So we have to figure out what this will be equal to. Okay, anyone have any ideas? What should we do? I think it's definitely reasonable to say that this can't really be 0, right? Just because this should be positive, this should be positive. Just set it equal to H, basically, is what you're saying? Yeah, there has to be a flow of heat, I would agree. Yeah. So this is going to be equal to the rate of heat flow. That's one of the things we want to calculate, right? So we want to find that, the rate of heat flow. This is going to be one of the things we need to calculate. But in order to do that, we need this temperature here, right? We need that temperature. So that there must be some other way to solve for it, right? What do we do? What do you all think? Are there any other equations we can write down? So you want to say that the heat flow through the steel, should be equal to the heat flow through the copper. Basically, what you want to do is instead of summing these, you want to say basically, let's take H steel and let's set it equal to H copper. That's what you want to try? You want to do that? Okay, so what's the logical reason for doing that? I mean, certainly good guess. So can we come up with some physics to back up why that might be true? Why might that be true? What's the 0th law? We did have the 0th law. What's the 0th law? Does anyone want to say what it says? What was the 0th law? What did it say? Two systems are in... Here, copy it. We'll copy paste it. That's the 0th law. Two things such so they're at equilibrium. Equilibrium, right. So what does that mean? Thermal. So that means that since these touch, they must be in thermal equilibrium with each other. And what does thermal equilibrium mean? The temperatures are the same, right? That's represented by this T being the same here, though, right? Okay, well let's go down this path right here, and let's see what happens if we take this path where we take H steel equal to HCU, and let's see what happens. And maybe the idea would be that, you know, if there's heat flowing into this point right here, and there's heat flowing out of that point right there, then they should be the same. That seems reasonable to me. I mean, it seems reasonable. Let's see. Let's see if we don't get a number that doesn't make any sense. We can always try things, and if the answer we get doesn't make sense, we can go from there. But I think this is a pretty fruitful way to go. Let's just see what happens. So we're solving for T. I have to do some algebra now. What's the best way to solve this? I guess just multiply things out, right? Just multiply it all out. I think what I'm going to do is move LCU to this side. So we're going to have LCU over L steel times K steel times A. And then we have to multiply that times 100. Minus, same thing. Oh, I'm gonna save myself a little bit of time here because the A's on both sides, right? So we can cancel the A's out. Cancel this out now. All right, so all I've done here is I've taken LCU and I multiplied it over here. So you have LCU over L steel times K steel times A times 100. Distribute that through. You have LCU over L steel times K steel times T with a negative sign. And we just need to get everything on the same side of the equation. So I'll do this in one final step here. Okay. Does that look right? Does the algebra seem reasonable? How are we going to get temperature out of what I just wrote? What are the units for K again? K is watts per meter Kelvin. I must have done something wrong. Times 100, that's what I left off. That seems more reasonable. Okay, I didn't get an answer yet, though. I mean, obviously I made that mistake, but do you all see any other mistakes that I made? Does that look right to you? Basically, all I did was I left this term here, right? We took this term right here and moved it over to this side, which made it positive. I factored out a t, and then I divided by the coefficients of t, which is this plus this. Does that seem reasonable to y'all? Check the math yourself if you want to. Okay, K for steel. Let's look that up. 50.2 is K for steel. And then we need to look up K for copper. 385. So L copper. Oh, whoops, the rest of the stuff's in the problem. So the length of the copper over the length of the steel is 0.02 over 0.1. And then that's multiplied by K for steel again, which was this number right here. That's it. Okay, I still haven't gotten it. Does this algebra work out right? Do you all agree? Am I confusing you all? By the way, I'm skipping these steps. It does work out? Okay, good. Alright, hopefully we don't get a crazy number. We don't. We get a number that's between 100 and 0. So I think that what we've done here is reasonable. I think your assumption that the heat flow through the rods needs to be the same is right. And I got an answer of T equal to... But you tell me what you get first, and I'll tell you what I got. That's also what I got. 20.7. 20.7 degrees Celsius. So that's the first part. And... now we want to find the rate of heat flow through the bars. And so we can use basically either one of our equations now, right, to solve this. So I'll just choose to use the one that has a 0 in it, as it has less things. So K copper was 385. Times the area, which we didn't use yet, 0.004. Getting this strange delay when I lift my pin up off of the... when I do this, and then I come back down, there's this... whatever, it doesn't matter. You all don't care about that. Okay. This, so we're doing K copper area. We need to multiply by the final temperature that we calculated, which is 20.7. Minus 0. And then divide this by the length of the copper, which was 0.02, or just 0.2, right? 0.2 meters. Oh, that must have been really confusing. It doesn't change the answer, but all of these, I did this wrong. I thought it was 2 centimeters. This should have been, I'll just go through here and erase them. This should have been 0.2, 0.1, and then 0.2 and 0.1. I apologize for that. Sorry, I made a mistake right here. In that and in this, when I plugged the numbers in. When I did the conversion in my head, I accidentally converted it. It doesn't change anything because it was a ratio. It's still just 2, but anyway. Made a mistake there, so check that in your notes. Alright, does this seem reasonable? Just to go back to what we did to solve this problem, we said, okay, well, we've got these two bars that are in contact with each other, and who was it? Was it Richard? Yeah, Richard said, Christian said, well, Richard suggested that we do this, which is correct, and then Christian said, didn't we have the zeroth law? And that was kind of the key to unpacking this, which is that that was a very good point, that if this is in thermal equilibrium, then that means that the heat flow through the whole object has to be uniform, or has to be the same. So, good usage of previous concepts. I want to highlight something else that I did here. So, did you all notice that I made this mistake? I didn't notice that I made this mistake. So, I went from this line to this line, and I was doing a bunch of algebra in my head, and so I made a mistake. And this is what I wrote down. I wrote this equation down right here. And I looked at this equation, and it felt wrong to me. And the thing that I noticed that was wrong, without even looking back to the algebra that I did, was that there's no way that you're going to get temperature out of these units here. Can you all see that? Because whatever the units of K are, they show up in the denominator and the numerator, right? So the units for K are just going to cancel out. And the units for meters over meters is just 1, right? So the overall unit, or the dimension of this quantity that I've written right here, would be 1. It doesn't have units. Can you all see that? That's right, Kelvin, yeah. Units will set you free, they will. It's pretty true. So I was like, there's no way this is right? And so that told me I need to go back to the previous line and figure out what mistake I made. And I was like, oh, there's this 100 here, and it didn't show up. So then I had to come in here and I had to write 100 degrees Celsius. And now, if I take something that has no unit and I multiply by Celsius, I get Celsius, right? So I can't emphasize enough that is really helpful when you're taking exams. It's really, really helpful on exams to be able to use that as a way to check your units, or to check your work, basically. I still use it, as you just saw, and I used it all the time when I took exams in college, grad school, everything. All right, so any final questions before I move on? We have about 15 minutes left, and we're going to talk about convection and radiation. Okay. Heat transfer. This is like the second method of heat transfer. First method was conduction. Second method is convection. And for this, we are just going to conceptually discuss how convection works without really doing any math. So convection is a heat transfer due to, does anyone know the answer? What's a heat transfer due to what? Conduction is heat transfer due to contact. Convection is heat transfer due to, so there are things called convection ovens. They work off of this principle, but what is the convection? It's the heat transfer due to the movement of a substance, so of matter, the movement of matter. And convection ovens are one example of this. Does anyone have a convection oven? I do not have a convection oven. At least I don't think I do. Anyone have a convection oven? Maybe you do and you don't know it. A convection oven is an oven. Oh, you do, Christian. What does it do? What's different about it? Can you tell everyone what's different about a convection oven versus a normal oven? Normal oven, it's got something in there that heats things up. It's loud, okay? It's very loud. Convection ovens are really loud, yeah. Normally ovens are not loud, right? My oven doesn't make any sound at all. Unless something starts to pop or anything like that. When you turn on the convection, the fan will start. Okay, so what you're telling me is that some part of your oven has a fan in it, basically. That's what makes your oven different from everyone else's oven, right? Is there's a fan in there, right? What that fan does is it forces air to circulate inside of the oven. And the circulation of air inside the oven makes it so that your food heats up very evenly. Makes it so that your food heats up very evenly, okay? Because most ovens only work off of what's called radiation. We'll talk about that in a second, but that's the type of heat transfer that does not involve contact. And sometimes, I'm sure, when you're cooking things in the oven, the top of something you're cooking can get burnt while the bottom isn't actually fully cooked, right? A convection oven tries to help with that. All right, well, since we don't all know what convection ovens are, it's probably easier to discuss convection using something that we do understand. So I'll give you two examples, boiling water and heating a home. So let's start off with boiling water, a very common thing that we discussed in this class. So let's say that I'm boiling some water on a stove, okay? So we've got a flame down here, we've got water, it's boiling, okay? So what happens here is that the water on the bottom is in direct contact with something that's hot, whether it be a flame or it could be a, electric stove where you've got that ring that heats up, right? It could also be possibly, do any of you have induction stoves or know what an induction stove is? Maybe not. That's okay. That's good. So let's just focus on two types of stoves. Stoves that have gas heating, like the normal just flame, or the normal kind of electric stove where you have like a surface that gets hot. So at the bottom right down here, we have conduction happening. It goes into, I'll use a different color. The heat is going into the bottom of the pot. The bottom of the pot heats up. Conduction goes to the bottom of the water, and you get really hot energetic water molecules down here. So all the water down here starts to get really hot, right? But energetic molecules, they tend to move upwards. You've probably heard the idea that heat rises. While it's not a very scientific way to say things, it is a good way to think about things, which is to say that hot objects tend to want to rise higher and higher, okay? So these water molecules, what they're going to do is they're all going to start to move upwards in the system. All these hot water molecules start to move up. And if they move up, then the cold water molecules from the top are going to have to fall back down. Right? So hot water goes up, cold water comes down to replace it. As these cold water molecules get back down to here, due to conduction, they heat up again, and now they're hot water molecules. And so they push up in this direction. And as a result, you get a circulation that occurs in your system. And that circulation of hot water to the top leads to even heating of the water. If it wasn't for the fact that the hot water molecules rose up to the top, only the bottom would really get hot, and then once the bottom of the water's hot, it would heat up the water above it, which would heat up the water above it, and that process would only be due to conduction, right? Only conduction. And if it's only conduction that's making it so that the water's heating up, it's going to heat up much more slowly than it would if the water circulates. So the circulation of the hot water to the top leads to an even heating of the water, and the substance, in the case of, so it's heat transfer due to movement of a substance, right? The substance that's being moved here is the water. The water kind of like rises to the top. Yeah, rolling boil. Yep. I'll give you another example of this, which is like in a home. If you have a house, okay, and let's say in your house, we're just going to look at one big room of the house, basically. Let's say in your house you have a radiator downstairs and there's vents in your home, okay? So you've got, there's a vent right here, let's say. And let's say that's where your heater shoots out hot air. So you've got hot air that comes in here. What does it do? It tries to rise to the ceiling. It pushes cold air down, and there's usually some type of other vent that can suck in, or even if there's not, it doesn't really matter. The idea is that this hot air basically rises up, and it kind of warms things up here. It pushes air back down, and it just kind of causes the air to kind of circulate through the home. And this makes it so that you don't have to sit right next to the vent to warm up. The whole house will warm up due to these convection currents. So we talk about convection currents because there's currents of flow through the air due to the fact that there's a hot source of air that's pumping air in. That air tends to rise up, it pulls down cold air, which then goes back through the system and gets heated up down here and just kind of just... That's convection. Does that make sense? Does it make sense why your convection oven's really loud? It's got a fan that's intentionally blowing the air around inside of the oven, and it supposedly does a really good job of heating food. I've never really had a convection oven, or I've seen them before, but I've never used one, so I don't know how good it is. But supposedly it makes it so that things heat up a lot more evenly when you're cooking food. Probably you can cook food in a convection oven faster too, Christian. Is that right? Is it faster? So I don't know what an air fryer is, but I keep hearing about them. Maybe I need to learn. Tell me what an air fryer is. What's an air fryer? What is an air fryer? How does that work? It's a mini convection oven. Okay. Can we go look it up real quick? 1 second. I want to see what these. Does anyone here have an air fryer? What do they look like? It's kind of like a toaster oven. It looks a lot like a toaster oven. But you can fry stuff in these things? Huh. But like you all are saying, it's basically just... It's just a convection oven, huh? Does it do the same thing? Is it really loud? When some of you have them? It's really loud, okay. So it's also pushing air around, yeah. It has fans too, now that I think about it, okay. It's funny, so it's called an air fryer, but really it's just an oven that has, okay. This is just this name that they've given to it to kind of help to sell it, okay. They're really popular though. I mean, I know so many people that like rave about how good they are. I usually put a foil under, but have to take it out because the air just blows it around. Okay, that's funny. The air prevents you from being able to put the foil down there because that's funny. Okay, so that's convection. We're not going to do any math with convection. It's just something it's important you understand that this is something that helps to transfer heat around. The biggest effect is going to be that it tends to make things heat up evenly. Convection can occur in all sorts of systems. It occurs in nature as well with high and low pressure, like heat waves that come in. Oh, so it is kind of frying things. From what Christian's saying, the frying process is about getting the water out of the food as fast as possible. Air frying does this by blowing the moisture away as soon as it escapes. Huh. That's interesting. So that means that it's frying things, but it's not frying things like you would if you deep fried something, right? I mean, if I take a piece of chicken and I put it in batter and I drop it into a bunch of grease, that's going to actually hold in the moisture, right? When you deep fry chicken. It's not a traditional... So it's supposed to be like a healthier way of frying things, basically, is the idea, right? Alright. Cool. Okay, one last thing to talk about. We don't have much time, but I'll just mention the last form of heat transfer is radiation. I had a few examples of this, but we'll just talk about radiation. There's some equations and stuff, but... They're pretty easy to use, so we'll just mention this. Okay, so last type of heat transfer is the heat transfer due to radiation. Radiation is the normal way in which things are cooked in your oven. So radiation is any type of heat transfer that doesn't involve direct contact. It doesn't actually require matter. Whereas conduction and convection both require matter. The heat transfer from the sun is radiation. So if I have the sun right here, right, and we have the earth over here, the heat transfer that occurs here through space, that's what we call radiation. That's what we call radiation. So you can actually think of all of these types of radiation occurring just by thinking about a campfire. I don't know if this is a good example for this class. I don't know how many of you have sat around a campfire. Really anything that burns. So the problem is, like, we don't have, like, a lot of people you don't have chimneys in this area, right? You don't have, like, fireplaces in this area. Maybe this is a bad example for this class. Have a lot of you sat around a campfire before at some point in your life? Yeah? Maybe a lot of people haven't, though. I should acknowledge that. So if you haven't sat around a campfire, all the things I'm about to say are true of a gas stove as well. But you can experience all the forms of heat transfer through this. So obviously, if you touch the fire, you're gonna burn yourself, right? But if you're standing, like, right here, right, and you're holding your hands out to warm your hands, and there's any kind of distance between your hands and the fire, then pretty much the heat transfer that occurs right here is radiation. Purely radiation, right? If, on the other hand, I stand above the fire, okay, and I put my hands above the fire, now you're getting heat transfer via convection. Because the fire is going to warm the air above it, right? And then that hot air is going to come up to your hands. You're going to get convection, really, and radiation in this case, though. Because sometimes you get both. And then conduction occurs anytime you touch it. Or, like I was saying, if you take a piece of metal and you stick it in the fire, right? Then you can have heat transfer through the metal that happens through conduction. So it's very common that all three of these things may be occurring in one scenario. Like I said, inside of a normal oven, what normally happens is at the top you've got these, like, coils that heat up, right? And then when they get really hot, they heat your food up. And those heated up by radiation, because the coils aren't actually touching the food. And the heat flow through the air isn't as strong as the radiative heat flow that occurs from the coils. In fact, you can kind of see down here in this equation, this is our equation for heat flow due to radiation. It involves area of the emitting surface. It involves the emissivity of the surface, which is a measurement of, it's a number between 0 and 1. It's the ratio of the rate of radiation from a particular surface to the radiation from an equal area of an ideal radiating surface at the same temperature, which basically just means this quantity is going to vary depending on what the surface is. Something like the sun probably has an emissivity really close to 1. We've also got this constant called sigma, which is this equation constant right here. But then look at this, the temperature of the surface in absolute terms. So this is in, this quantity, T, is in Kelvin. So it could be a very big number. It could be like 400 Kelvin or something like that. But notice that it's raised to the, I don't know if you can see this very well, it's raised to the 4th power. Temperature to the 4th power. So the sun, if the sun has something like a temperature of, let's say, 20,000 Kelvin, the heat transfer, you get to multiply by 20,000 to the 4th power, which is a huge number. So the bigger and bigger the temperature gets, this starts to become a huge amount of radiation. And apparently with the sun, it's enough radiation to keep our planet warm. And, the sun is going to keep burning for the next 5 billion years plus before it turns into a red giant. And it's just this thing that sits there and constantly radiates energy to our planet. Almost all forms of energy on our planet can be derived from that energy that came from the sun, in the form of the wind currents that exist on our planet are due to temperature differences. That wind energy can be harnessed. The kind of cycle of water that freezes and then melts and then flows in rivers that can be harnessed via hydroelectric dams is part of this. Obviously, solar energy itself can be converted directly through photoelectric panels, through solar panels, into energy. So the sun is kind of the source of most of the energy on our planet. Even the oil that we use comes from beings like dinosaurs that walked the planet and soaked up the sun's energy by eating the plants that are around it that were raised by the sun, and then after they died, they decayed and produced these oils that again can be tied back to the energy that came from the sun. Without the sun, our planet would be utterly lifeless, you know? Utterly lifeless. There would be just rocks, and obviously with no sun, you can't have water, because it needs to be able to melt and stuff like that. So all through this radiative process of energy flowing through space, through the emptiness of space, do we get life on this planet and all the energy sources that we rely on to power our devices and stuff like that. Okay, that's where I'm going to stop today. I believe next time that we meet will be for the exam, and then next week we're going to move into talking about ideal gas law, kinetic theory of gases, stuff like that. So just remember, on Wednesday morning, show up on time. You're going to have 3 hours for the test. It shouldn't be too hard. Shouldn't be too hard. Make sure you study, review your homework, look over I think reading the textbook, it's 2 chapters, right? Reread the textbook, it's only 2 chapters. Might as well, right? At least skim through it, look back at the example problems, see if they make sense to you. Yeah, so that's all for today. Hope you all have a nice day, and I'll see you next time. Yeah, the lab manual is due next week. I'm going to go ahead and stop the recording.